Additional okay, I suppose we will jump into it. I just now noticed that I like when I'm lecturing here, I get to watch the sunset, which isn't that magical. Yeah, or yeah, maybe it just burns into my eyes because the sun shines in. But either way, that's basically magic, though, right? Okay, so a couple of quick announcements. I did post the big group project that I was talking about, along with the Python project files, so you can take a look at that, and I've got all the details in there. The first three questions, probably historically, I've given those exact same three questions before, modified a little bit, and everyone thought they were fine. So everyone should probably find those okay. It's the binary search tree, the one that I'm like, maybe not. You'll let me know, I'm sure. I've also posted the chapter review assignment for this section that we're finishing today. The course outline says it's due on Saturday. Obviously not, because when I was building the course outline and adding the due dates, I kind of forgot that we lost 2 Mondays of class. So, that due date was under the assumption that we weren't losing the class time, so it's not accurate. So it's due next Saturday. So it's already up, but it's due, next week, end of it. So you got lots of time to work on it. Because really, I don't care when they're due for the most part. So might as well give you an extension, essentially. But I think that's all I have for that. So I guess we'll just jump straight into it so I can give you your favorite Wednesday gift. I guess, yeah, related. We don't have class on Monday, obviously. So there won't be a quiz next week because I'll be talking about one thing. So it would just be due the next week after, probably. So yeah, I'm going to have to do some fudging and adjusting of schedules for the missed Mondays, but that's light. So last class, I talked a bunch about probability, which I understand is a kind of dry topic. The one we're talking about after this is linear algebra, which, people probably also find that dry too. But it's less elementary, so it's not really high school review anymore, so people tend to find that more interesting, whereas everything I'm talking about here, except maybe conditional probability, people are like, yeah, I saw that already, and many times. And I'm going to continue that trend. We're going to talk about combinatorics and counting. But we just went over basic probability principles, like what is probability, some common pitfalls related to it, and then some examples for computing it. And then we did this conditional probability one, but I just wanted to start off with an example related to it that I, again, stole out of a statistics textbook, but I think this one is probably made up because it does not match my experience doing this exact thing. But that's the fun thing about statistics, is my experience is not indicative of a trend. So suppose you were traveling from, Toronto to Edmonton, to Toronto, from Edmonton with a connection in Calgary. Obviously by flight, right? Because why would you? I guess you could take a bus, but the probability your first flight leaves on time is very low. Which this is why I'm saying I don't think that's true. I've flown out of Edmonton a lot of times. It's not Yeah, I've had like 1 or 2 flights delayed, not most of them. So okay. Oh, sorry. This is on time. So a 20% chance that your flight is on time. Yeah, I don't think so. If the flight leaves on time, then the probability your luggage arrives with you is, I think, percent. Although again, I've flown like 50 times and I've lost my luggage twice. So anyway. But if it's delayed, the probability is 0.5. So this makes sense, right? You've got a delay in your flight, your luggage is less likely to make it there with you, right? Because it gets lost or confused or whatever. So we want to answer some questions about this, specifically some other probabilities. So what is the probability of your luggage arriving? Then what is the probability that your first flight was delayed given that your luggage did not arrive? So these are things we want to figure out. Now, one of the things that can be helpful with sort of conditional probability, especially, is building sort of a probability diagram or a tree. So, we've got this main event here. Doesn't really matter what it is specifically, but there's sort of 2 branching conditions here, right? Either for our first event, our flight is on time or it's not. So on time is a 0.2 chance. And then from there it branches again. And this is delayed, which again branches there because the second thing that happens is whether or not our luggage made it. So we know the probability of it being on time, so we need to know the probability of it being delayed. So that's just 1 minus the probability of it being on time, right? It's the sort of opposite event. So this is 0.8 is the probability of being delayed. Now, we read here, if it leaves on time, then the probability your luggage arrives is 0.75. So luggage is 0.75. Can't write or spell or anything. So that means it not arriving is 0.25. Because it's, again, 1 minus that. Now, if it's delayed, it's 0.5. And no luggage is also 0.5. So we've sort of got this tree, right? We can sort of traverse it to figure out the probability of events happening, right? Like what's the probability of my flight being on time and my luggage being with me? We just multiply them together along the tree. So that means the probability of our luggage arriving, there are sort of 2 ways to get to the question, did our luggage arrive? And that's our flight was on time and then our luggage arrived, or our flight was delayed and then our luggage arrived, right? Those are the 2 situations of our luggage arriving. So that means we could just sort of add those up. So on time, which is 0.2, going across this path, times 0.75, plus the sort of other distinct path here. It could be delayed, and the luggage arrived. So this is whatever number it is, 0.55. Okay, so you know, regardless of whether our flight was delayed, our chance of arriving with our luggage is 55%, which again is pretty bad. So then this question is, what is the probability of our flight having been delayed if we are standing at the airport without our luggage? So you arrive there, your friend's there to pick you up, and you don't have any luggage, and your friend's like, flight was probably delayed, huh? I mean, your friend probably knows that anyway because you would have communicated that. But anyway, this is a conditional probability. So we need the probability of delay and no luggage. And we also need the probability of no luggage. So, okay, well, we did just figure out this bottom one in a sense, right? We just found the probability of luggage arriving is 0.55. So the probability of it not arriving is 1 minus the probability of it arriving, right? It's the sort of contrasting event there. So what's the probability of delay and no luggage? Again, we just go through this path, right? Delayed, no luggage. 0.8 times 0.5. So then I plug this into my calculator because I am too lazy to divide fractions. So if you're standing there without your luggage, the chance that you arrived there on a delayed flight is 89% almost, right? That's what that means. So very high degree of certainty that you arrived with a delayed flight. So now a question is your luggage arriving independent from your flight being delayed? And no. So is your luggage arriving independent of a delay? So what that's saying is the probability of delay given no luggage oh my god, the same thing as just the probability of delay. Well, this first number is what we just found. And this number, delay, is 0.8. So they're not the same thing. And I mean, this is sort of to explain we had that weird definition of independence, right? These two things being the same for events to be called independent. So if we think about it, just from experience, your luggage arriving with you on a flight and whether or not it was delayed, those are generally related, right? The two situations where my luggage was missing or when my flight was delayed. So generally speaking, if your flight is delayed, you are much more likely to not arrive with your luggage. They'll probably say, hey, it's on the next flight. So it'll be here in 4 hours or whatever. But that does mean it doesn't arrive with you. So it makes sense that those events aren't independent, right? If they influence each other. If one happens, then the other is more likely. And this is sort of the mathematical encapsulation of that. This is saying, hey, these two numbers aren't equal, so they're not independent, right? So that makes sense. Okay, so I just wanted to finish off with an example on conditional probability that's maybe, I mean, the numbers are, probably you wanted the numbers to be accurate. Maybe it's higher than that, but it explains the philosophy anyway, even though the numbers are probably not so accurate. Okay, so we're just going to have a brief foray into combinatorics, and I'm not going to spend too much time on this again because it is something that I know is covered in both 30-1 and 30-2, so if you end up needing it, well, you have the skills to look it up, but I just want to make sure we talk about it really quick. And that's the idea of counting in combinatorics. So when I say counting, I don't mean, 1, 2, 3, 4. We all know how to do that. Although if you tell me to say the alphabet backwards, I have to really think about it. So don't do that. But counting, we can all probably do. So when we say counting, we usually mean things that are exceptionally large, right? And that would come in here when we're talking about these probabilities, because we need to know how many distinct outcomes are there? And, rolling a die, okay, there's 6 outcomes, but what if you had a very complicated way to determine your outcomes? And you're like, okay, well, how many are there though, right? Like, you're choosing a bunch of different letters from the alphabet, but certain positions of the letters have to follow certain restrictions. And, you need to think about how many do I have? How many passwords do I have? How many license plates do I have? That sort of thing, right? We want sort of a formula way to count rather than just literally counting them. So that's what we mean when we say counting. And a lot of the rules are the same, so I'm not going to write this down on the board, other than just saying the sort of summary. For counting, we multiply counts when they're independent events. Are independent. And that means either this definition or just the intuitive definition, right? Flip a coin, roll a die at the same time. I mean, as long as the coin's over here and the die's thrown over there, they don't influence each other, right? They're completely separate events. So then the number of outcomes would be 2 ways to flip the coin, heads or tails, and then the die, 6 possible faces. So the total number of outcomes is 2 times 6, which is 12, right? If, when we're determining outcomes, you can identify situations where you're faced with a decision and you fall into exactly one of the cases, so they're mutually exclusive. Where you fall into precisely one category, you add outcomes. So the example I have in my notes is I go to a bakery, right? I'm buying one single item. There are 7 choices of bagels and 11 choices of donuts. I have 18 possible things to choose from, right? I add those up because I'm buying one of them, so they fall into completely distinct categories, one or the other. So you add them up. So this is sort of a general rule. It matches probabilities, right? If you see the word and, it's usually what we say when we're talking about independent things, you multiply them. If you see the word or, you add them. So I can choose one of 7 bagels or one of 13 donuts, right? So add them up. General rule. So an example of an application of this, and I'm going to have to write a lot. I think that's probably why this is just like this, is there's a lot of writing. So I could probably do something about that, but right now. So we're going to talk about license plates. So in Alberta, we have essentially 3 different types of license plates that are available to people. We're not counting like vanity plates where you can put whatever you want on your plate. There are 3 general categories of license plates. So the first one is just regular plates. You probably have one of these. And there's sort of 2 different, you might be assigned one of these 2 different situations. I don't know what they use to decide it. So they either have 3 letters, then 3 digits, or 3 letters, then 4 digits. Where the letter aren't the following A, E, U, or Y. There are also veteran plates. They start with a B. And I think it's 2 letters, 2 digits. Then 2 letters, 2 digits. And lastly, there's motorcycle plates. That's 2 letters, 3 digits. And also, you can probably figure out why no plates can have O or I. You could probably imagine why, because I mean, this is how we would write I, but from a distance, when you're trying to identify a plate, is that an O or a 0? Is that a 1 or an I, right? So that's why we don't allow those. Most places will probably have that restriction. Okay, so our goal then is how many possible license plates can we have? And this is an important question to ask, because if you run out of license plates, then when people buy vehicles, you can't go to the registry and say, sorry, we're out of plates, so you don't get one, right? You would want to design this so that it sort of allows for a lot of license plates, right? Like, what is the population of Alberta? Like 10 million, 15 million, I don't even know. So let's just say literally every single person had a vehicle. You'd probably want to account for that, right? Lots of people have more than one, but then some people don't have vehicles at all. So it probably works out that you'd want to have at least the population of people able to have a license plate. So this is a pretty basic, what I would say, counting argument. So for this regular plate situation, our plate looks like this, right? It's 3 letters, then 3 digits. So how many letters are there? Yeah. So this is 1 of 26 choices, right? 26 choices here, 26 choices there. How many digits are there? 10. Right, so the total number for that first one is 26 to the power 3 times 10 to the power 3. You multiply these all together because it's an and, right? You have to choose this number, this letter, and this letter, and this letter, and so on, right? They're not distinct choices. However, what is a distinct choice is the next type of plate, right? You're either getting this plate or this plate, right? So you one or these. So whatever this number is, we add it to the total that we get from this number, this type of plate. So again, this is 3 letters followed by 4 digits. So we already know that there's 10 digits to choose from. But how many letters do we have? Oh, sorry, it's not 26. Yeah, the 2 letters that we don't want to include in any of them. So it's actually 24. But now same thing here. How many letters do we have to choose from? Well, we take those 2 out, and then we take another 4 out, so we have 20. 20 to the power 3 times 10 to the power 4. Now we look at the veteran plates. So they look like this. Always start with a V. So that doesn't contribute to adding anything, right? So again, we have 24 choices. And then 10 choices here. So this is 24 squared times 10 squared. And then our last one is motorcycle plates. So 2 letters, 24. each, and 3 digits, 10 there, 24 squared times 10 cubed. Right, and that's a pretty basic counting argument, right? You just figure out, okay, this is my pattern. What can I put into that pattern, right? And then you multiply all of the possibilities together inside that pattern. And then if there are multiple different types of patterns that you fall into, you add them up, right? So the number of license plate is whatever this number is, all added together, which I shockingly cannot do in my head. So this is 1382400. We want to use separators. That's 13 million. So already we're in good shape. This is 8 and a bunch of zeros. 1, 2, 3, 4, 5, 6, 7 zeros. So also a lot. This is not too many, but that's probably fine. And this one is 76000. And this is a really big number. 9445760. I feel like I did a bad job with my commas here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I just made a typo in my calculator here, because right here I say this is like pretty big. This number, these obviously don't add up to each other.
Could the second one be 80 million?
That's probably where I made the typo then. I just didn't type enough zeros. And now it makes sense. Thank you. So the point is, we have a lot of possible license plates, right? We're probably not going to have to worry about running out of them, right? So, you know, that's like if you go dig around a barn somewhere and someone's like, oh, yeah, it's license plate from like 50 years ago. It probably hasn't been used again, unless the person used it for multiple things. But generally speaking, we can probably assign a unique license plate to a person and they can just keep that license plate forever, right? And we won't have to worry too much about running out of them. And it's actually really easy if we ever did. We're just like, oh, okay then, add another number, right? And now we've just increased. Now there's 8. Now we just added like, 720 million. So that's a lot, right? So this is just a sort of mundane example of how many possible license plates, but you can imagine if you're trying to figure out, okay, you're designing a website and you're trying to come up with password restrictions, right? You're like, okay, well, you know, I want to impose some kind of restriction on my passwords, like you have to have a special character and yada, yada, yada. You ask how many possible passwords are there, because that's a part of security, is knowing what the possibilities are. And generally speaking, for that, you would want to know the minimum possible. So like if you say, okay, you need to have a password of 8 characters, then it's like, okay, most people are going to be lazy and have a password of 8 characters because they don't want to remember more than that. So how many possible passwords fit into that scheme? And you'll see quickly how easy it is for someone to brute force a password. Because you'd want that to be relatively large so that it's not worth it. And actually, I'm sure you know this already, but hacking is the most mundane thing ever. It is not some 90s guy sitting at his computer in like Matrix style outfits typing at it. No, it's just sending an email and saying, hey, I'm your trusted person, give me your password. And it works. Social engineering is extremely effective. That's what hacking is. It's phishing. It's stealing information from people who give it to you willingly is what hacking is. Which means this sort of analysis on password security is more for, computers have become a lot more powerful. So if you want to brute force a password that only has like 10 million possibilities, that doesn't take very long anymore. Okay, so another related concept is that of a permutation. a permutation is an ordering of distinct items in a line. So specifically, it means when we're ordering our things, the order matters here. So if I did so the letter is like A, B, C in a license plate is not the same license plate as B, C, A, right? Those are different things, right? We care about the order in which we write these things. So that's what this is sort of encapsulating. So I'm going to write this in the mappy way. Our permutation of n objects is an arrangement of R of all those objects from the n that we have, and we have a formula for finding the total number of ways to do this. Ways to do this is a formula that you would have pressed a lot in high school. N factorial over n minus r factorial, or on your calculator, the NPR button, right? That's what this one does. So it's just a fast way to evaluate this formula. Although on on my computer, typing this is probably faster than digging that up these days. But on a calculator, there's a button for that. So as a quick example of where this would matter, it's in arrangements of things where you care about how they're arranged. So suppose 36 people are attending a workshop. You know what, let's say this. 35 people with you. Other people. There's 36 total. So they are all seated at 6 tables each with 6 people. Okay, so pretty standard. There, you're sitting at a conference and there's just a bunch of tables and you sit at them. But you went with 2 friends and you want to sit with them. I want to sit with my 2 friends. At a table. So then a question is, how many possible seating arrangements are there? Well, probably a lot. How many seating arrangements? So the first thing to notice is how many ways are there to arrange my friends and I? Well, there's 3 of us. So first, arrange myself. So, you've got 3 different places to sit. You sit somewhere, a friend sits somewhere, and the other friend sits somewhere, right? So there are 3 factorial ways, which is 6, right? Because in this situation, you choose one of the 3, can't choose the same one again, so now you choose 2 of the remainder, and then you choose the last one. Okay, so there's 6 possible ways to arrange ourselves. So once seated, there's 33 other people who could sit at the table. So what we have to do essentially is choose 3 of those people from the 33. We wish to select a random arrangement, or not really random, an arrangement of 3 people from those 33. Right? Because there's going to be 3 specific people, and we want to pick an arrangement of those people. So, I mean, there is a formula for this, but you can also intuit it, right? So you've got these 3 other people you need to pick. Well, there's 33 people to choose from. So choose the 30 out of the 33. There's only 32 left, and now there's 31 left, right? Okay, but what does this formula tell us? So we've got 33 P3. So that's 33 factorial over 33 minus 3 factorial over 30 factorial, which is 33 times 32 times 31. So this formula matches sort of our intuition here. And this is, so total is whatever large number it is. 6 times 32736 96416 total people or total arrangements. So, at a conference with this many people, there's a lot of random situations you could get into. You could sit next to a lot of different variety of people in a lot of different orders. So permutations, though, care about the ordering, right? So person A, B, and C, we're saying that's a distinct seating arrangement from person B, C, A, right? They count as different things, even though in terms of meeting people, it would be the same outcome, right? You're sitting with the same 3 people no matter what. So there is a sort of related concept that sort of doesn't care about that ordering. And that is the idea of a combination. There it is. An R combination of n objects is just a subset of R objects from n. So we no longer care about the order. No longer matters. Okay, so the formula, this is in CR, which you've probably seen also. It's almost the same thing, except now we just divide by R factorial. So essentially we're dividing out the number of ways to arrange the R objects. We're saying, hey, we no longer care about the distinct orderings of them, so let's just remove those possibilities, and then we get something that works out nicely. So the notation also, you might have seen, is this. This is calculator notation, which maybe they use in high school just because they know you're going to use a calculator. This is the more math-heavy notation, so that's the one I gravitate towards. So let's do some examples of this. There are lots of situations where you don't care about the ordering. In fact, there's a reason why this has, I only wrote down calculator notation. There really isn't any other notation. But this one, there is a symbol for it because this one comes up way more often, right? This is the one that we actually care about is how many ways are there to make a set of R objects from n, right? Okay, so your friend is holding 3 cards. From a deck, a regular deck. don't know cards, that's 52 cards, 4 suits, 13 cards in each suit. We're not including jokers. So pretty standard stuff. Your friend tells you they are all hearts. And also, at least one of them is one of the 2 highest cards. So that's ace or king in this case. So how many possible sets of cards is your friend holding, right? Your friend just said, hey, I got some cards. Here's a condition on them, right? So we just are wondering how many possible ways are there to, how many hands are there? So the way I think about it is your friend has said, I'm holding 3 cards, and at least one of them is either an ace or a king, right? So 2 situations. Friend has an ace, right? Because your friend is saying, I'm holding one of the 2 highest cards. Or your friend has a king, but not an ace. So we're going to sort of split this up into cases and sort of think about how many possibilities there are. So in this case, your friend has 2 other cards in hand, right? You've got your ace here, and then there's 2 other cards to choose from. So we don't care about the ordering, though. So it's not entirely accurate to just fill those in. We're going to use the formula. So this is 12, choose 2, right? And that's apparently 66, which I can't do in my head. So the first card was selected. We don't have to worry about it. After that, there's 66 possible choices. One of them could be a king. That's fine, too. We just know that ace is the highest, right? Now your friend has a king, but not an ace, and this is basically the same thing. We know that these other 2 cards can't be an ace or a king. So 11, choose 2, which I think is 55. So total, 66 plus 55, 121. So your friend has 121 possible hands that they could be holding. So naturally, this sort of thing comes up in card counting, right? Actually, poker as a game entirely revolves around this, right? You use this sort of counting technique to find the odds of getting a specific hand, and the lower the odds of getting that hand, the more valuable it is. That's literally the ordering of hands in poker, right? The least likely hand is the best, and the most common hand is the worst. So a pair is the most common, and a royal flush is the least common. So let's just do one quick example. So we're going to say odds of 4 of a kind in poker. And I know there's lots of different variations of poker. 5-card stud. Okay, so if we're making 4 of a kind, well, first we need to choose that kind, right? We're saying we're getting 4 of the same card, so like all 4 8s or whatever. Choose the kind. So we ask ourselves, okay, we're choosing one of the face cards from the 13 available. Okay, now we've done that. So what do we need to do? Well, we're choosing 4 of the cards with that face value. Hold on. Yeah. Now, choose 4 of the 4 cards. Kind. So, I mean, it's kind of mundane. 4 choose 4. Right? There's 4 cards, and we're choosing all 4 of them. And we have 1 card remaining. So there are 48 cards left, and we're choosing 1 of them. So all told, this is how many possibilities there are, and apparently that's 624. So if we wanted to figure out the odds of this hand, or probability, well, we've got this number here, 624 that we just found. That's the positive outcome. We have to figure out how many total outcomes are there. Well, there's 52 cards. We're choosing 5 of them. Right? That's it. Which the odds are 1 in 4,165. So 4 of a kind, pretty rare. So we can do a similar thing for 3 of a kind. Same exact argument. So we choose 1 of our kinds. And then from 4 cards, we're going to choose 3 of them, right? Now, it's tempting to say, okay, from the 48, choose 2. But there's a bit of a problem with that, and it's that this allows for those 2 cards to be the same thing, which is actually a different hand in poker. So, you know, if you had king, 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 queen, queen, it's called a full house. That's a different hand, right? So we don't want this situation. We want to make sure that they are different cards. So from, I don't want to write this. Yes. So this is saying, okay, we're choosing different cards from the remaining 12 faces that we're choosing 2 of, right? This is sort of just guaranteeing that these are different cards. And then all this over this exact number again. And there's another big number. 88 over 4165. So again, you can kind of just use this argument to count all kinds of poker hands. You just have to think, okay, what am I actually selecting, right? So I'm choosing 1 of the kinds, and from that kind, I'm choosing 3 of them. It'd probably be better if I swap the order of this, actually, for explanation. So I'm choosing 1 of the kinds, so let's say king, right? From that, I'm choosing 3 of them, so 3 kings. Now, I am choosing the remaining 2 kinds, so let's say a queen and a 5, right? This right here ensures that I'm actually selecting different things, right? I'm saying from 1 of those choices, or from 4 of those kinds, right? Because there's 4 queens, choose 1, and from the other one, choose 1. Right? If we didn't have these, then it would be, okay, well, I could choose queen, queen. Right? We haven't removed that possibility without these steps there. Okay, and so again, I think I do a lot of these computations in the note. If you wanted to check more, there's more. So with that, I will say, hey, we're done with probability. So again, who remembers seeing this notation? Maybe not how to do it, but like Yeah, right. Like if there's one thing that's like burned into our brains from high school, it is probably this. Like I remember like half of my diploma exam consisting of this. Like honestly, it was a lot. So that's why I'm like I kind of hand waving my way through it. You've all seen it, and I don't need to emphasize it, right? So it's not super important at the end of the day. So I'm not going to spend too much time on it. It's just you might need to count things sometimes in programming. Just think of all the possible situations you might find yourself in, or you're trying to iterate over a loop and you're like, oh my God, how big do I make this? Well, you might need to do some counting to figure out how many iterations to do. And so that's why it's useful. But that's very basic stuff that you'll probably have to do. So with that, I will give everyone their favorite gift.